In the previous example, we estimated the instantaneous rate of change in the function h of t equals negative 16t squared plus 20t plus 400 at t equals 3 seconds by calculating average rates of change over shorter and shorter intervals. If we were willing to do a bit more algebra, we could automate this process. The algebra I'll show you in this example will be crucial for when we start calculating derivatives of functions using the definition of the derivative. Write a formula for the average rate of change in the function f of t equals negative 16t squared plus 20t plus 400 on the interval t equals 3 to t equals 3 plus h. Note that I changed the name of the function to f to avoid confusion with the variable h, but it's the same function as the previous example. Also notice that instead of asking for the average rate of change over a fixed interval, the interval from 3 to 3 plus h can be any length depending on the size of h. This will be the key idea behind our definition of the derivative later because it will allow us to let h get smaller and smaller to make our average rate of change approach the instantaneous rate of change as h approaches 0. For now, let's just focus on how to do the algebra. The rate of change in f from t equals 3 to t equals 3 plus h is the ratio f of 3 plus h minus f of 3 over 3 plus h minus 3. We've already calculated f of 3 by just plugging in 3 for t. F of 3 equals negative 16 times 3 squared plus 20 times 3 plus 400, which equals 316. Evaluating f of 3 plus h is more complicated because we won't be getting just a number. We'll get an entire expression. Just like in the example where we first used a formula to evaluate a rate of change, I'm going to replace every t in the formula with an empty set of parentheses. And then I'll fill every set of parentheses with the desired input, 3 plus h. So f of 3 plus h equals negative 16 times 3 plus h squared plus 20 times 3 plus h plus 400. Expanding and simplifying this expression is going to put your algebra skills to the test. While it is tempting to take shortcuts, I encourage you not to. In my experience, nearly every student who tries to skip a step ends up with the wrong answer. My recommendation is that you start by rewriting 3 plus h squared as 3 plus h times 3 plus h. This will trigger your prior knowledge about how to multiply binomials. You may have learned a technique like FOIL or something equivalent, and it will reduce the temptation to incorrectly try to distribute the exponent. This would be a great time to pause the video and try to do the algebra yourself. Then, when you're ready, press play and see if you end up with the same result as me. To begin simplifying negative 16 times 3 plus h times 3 plus h plus 20 times 3 plus h plus 400, I'm going to use the FOIL method to multiply out 3 plus h times 3 plus h. F stands for first, so I'll start with the first term in each binomial. 3 times 3 equals 9. O stands for outer, so I multiply the 3 from the first binomial and the h from the second binomial to get 3 times h equals 3h. I is for inner, and h times 3 is 3h, and L is for last. H times h is h squared. I'm going to be very careful to keep all these terms in parentheses so they don't forget to distribute the negative 16 from out front later. Before I start distributing, it helps to clean up the inside of the parentheses as much as possible. In this case, I can't do much, but I can combine the like terms of 3h plus 3h into 6h. So I have negative 16 times 9 plus 6h plus h squared plus 20 times 3 plus h plus 400. Now, when I distribute the negative 16 and the 20, I get negative 16 times 9 plus negative 16 times 6h minus 16h squared plus 20 times 3 plus 20 times h plus 400. Negative 16 times 9 equals negative 144, and negative 16 times 6 is negative 96. So this is equal to negative 144 minus 96h minus 16h squared plus 60 plus 20h plus 400. Again, I can combine like terms. This time, I can combine both the constant terms, negative 144, 60, and 400, and the h terms, negative 96h and 20h. Negative 144 plus 60 plus 400 equals 316. And negative 96 plus 20 equals negative 76. So the simplified expression is f of 3 plus h equals negative 16h squared minus 76h plus 316. We are finally ready to plug this expression in to our rate of change formula. Using that f of 3 plus h equals negative 16h squared minus 76h plus 316 and f of 3 equals 316, f of 3 plus h minus f of 3 over 3 plus h minus 3 is equal to negative 16h squared minus 76h plus 316 minus 316 all over 3 plus h minus 3. Notice that when we simplify, the 316s cancel in the numerator and the 3's cancel in the denominator, leaving just negative 16h squared minus 76h over h. This is a good sign. In fact, the first time I worked this problem, the 316s didn't cancel, and that let me know that I needed to go back and check my work. It turns out I had forgotten about the 60 in an earlier step. Now, because every term left has an h in it, we can factor an h out of the numerator and cancel a factor of h from the top and bottom of the fraction. Notice that I'm using the word factor a lot. You can only cancel factors from the top and bottom of fractions. It might be tempting to cross out terms, but that's never correct. To make sure you never cancel something you shouldn't, remember to always factor before you cancel. When I factor out the h, I get h times negative 16h minus 76 all over h. Then notice that because there is just an h in the denominator, when we cancel it out, it leaves behind a 1. But dividing by 1 doesn't do anything, so we can write the expression as just the numerator, negative 16h minus 76. Our final expression is a fast way to calculate the average rate of change in the original function, f of t, from t equals 3 to t equals 3 plus h. To use it, we can just plug in the length of the interval we want. like say h equals 0.01, for example, and it outputs the average rate of change. We will see later, though, that the real power of this expression is that we can now plug in h equals 0 to find the instantaneous rate of change at t equals 3. Negative 16 times 0 minus 76, which confirms our estimate from earlier. There are a lot of technical details, of course, about why we can do this, but we will learn all about that later when we talk about limits. For now, I just want you to know why these expressions are so important.